Hello, good afternoon, and welcome to this Tech Talk on tangible functional programming with Connell Elliott, formerly of the Microsoft Graphics Research Group, where he worked for several years, and now he's been working on this for several years. So welcome, Connell.
Okay. Am I on? Is the mic on? You can hear me? Okay, cool. Well, thanks for coming. Glad to be here. I want to encourage interaction. It's more fun for me to give a talk when people talk back. So feel free to ask questions or raise objections or whatever. Yeah, that makes no sense at all what you're saying. Whatever. So it just makes it a little more fun for me. And for people who are video conferencing in from other sites, if you want to ask a question or have something to say, just unmute your mic and then dive in. Interrupt me. So I'm going to be talking today about what I call a modern marriage of usability and composability. In a particular incarnation, tangible functional programming. So we live in this world of software, and it occurs to me that we have a fundamental rift in this world we live in, and that is between using software and making software. Okay? So we have these two halves. On the one hand, there's using software, and so all the values there are sort of user-friendly values. And so we have things like, well, it's humanly usable. Somebody can interact with it. Also that it tends to be concrete and visual. So it's a sort of a right brain visual immediate world. That's what we go for, especially these days with GUIs. On the other hand, on the other side of the schism, we have the programmer-friendly half. And the values and properties there are quite different. And there we go for composability. That's what makes us really powerful. So programmers have access to this very, very powerful means of communication. And composability is at the very heart of it. That's how we make more complex things out of simpler things. And the properties that seemingly go along with that to support it are syntax and abstraction, as opposed to, say, something visual and concrete. So why do I even bother bringing this up? Well, it's because I think that there's serious drawbacks, that each of these two halves have properties that are of immense value to the other, and that we're losing those. And so here are some examples of that, which is that when I shift from a library, an API, over to an application, I've lost a tremendous amount of access to functionality. So it's very fine-grained access to functionality in a library. You can call any of the API calls with any arguments you want. And hopefully there's a type system that sort of mediates it, makes sure that you're talking some sense. But there's this great fine-grained access. And on the other hand, and sort of going along with that, is that applications generally are not composable. So an application you can think of as, you can think of a library as a means to an end. All right? So a software library is a means to an end, and the application is the end. But it's not only an end, it's a dead end. So I have this wonderful composability, all this expressiveness, all this inventiveness at the level of the library. We wrap it into an application, which is the thing we give away, and now it's a dead end. It's no longer composable for the most part. So there's a terrible, terrible loss. Then on the other hand, looking at libraries, well, they're generally not very user-friendly. So they're friendly to a very small population, sort of educated engineer, right, left brain, sequential type thinkers. And so there's a tremendous subset of the population, I'd say most of the population, which is left out in the dark and aren't able to communicate through this tremendously powerful medium, which I would suggest is a more expressive and more profoundly important medium than the written word. So the medium of computation. So this is very important to get past this age of illiteracy where only a kind of highly educated, and not just highly, but particularly educated priestly caste can express themselves and pass their ideas down. And I would say that we're not only leaving out some people, but more importantly for humanity, we're leaving out what these people would say. And I would say a solution is not teaching them Visual Basic or Java or something like that, because we actually change the way their brain works. We change their creative process in doing that, and they no longer say what they would have said. So that's sort of a picture of how I see the context where we are now. And what's the dream? Well, the dream is to take the best of both of these two halves and build this rich, rich, accessible entryway into the medium of computation that has these two properties of it's usable and it's composable. And when I say composable, I just mean distilling down. That's the essence of what we programmers get to do. That's what makes what we do so powerful. So, any questions? I'm going to get into more technical stuff. That's fine. So here's a, yeah, go on.
Meta, you said applications or data. What about meta applications like Automator on OS X?
So is this an application builder? Just so I...
In a sense, yes.
Okay, so the question is, what about meta applications? And you gave a particular example, which I'm not familiar with. So is it, what does it do? Just so I know what you're talking about.
Automator presents you a list of other applications and actions you can do on them, and allows you to basically build scripts in a visual way.
Great. So here's an example of a sort of app builder that gives you some sort of visual interface, an interface to what are the entry points that are accessible and how do you get information in and out of them. Is that sort of an example of what you mean? Yeah, okay. So that's a great example of something that tries to bridge these two worlds. So now, I'm not saying that we never do that. I'm going to describe a way to do that, and I'm guessing, and I'm only guessing because I don't know this application, I'm guessing that the way they'll describe find simpler, more systematic, and more complete. But I'm shooting in the dark there. Okay. So where else have we seen this, at least an attempt to bridge these two worlds? Where else have we seen something that is both usable and composable? Well,
so there's the morphic framework in Self and eToys. There's ToonTalk. There's been a bunch of visual systems which are simultaneously user interface systems and visual programming.
Yes. Yeah. So the world of visual programming has addressed this sort of space. And I want to suggest that they're doing something, well, I was going to say wrong. I'm doing something rather different. And in about 2 slides, I'll say what that is. Okay? I'm going to move on now. So I'll give you another hint. Where have we seen usability with composability? So it's Unix and Unix pipes. So this is the classic beautiful vision of Unix. Small is beautiful. And the idea was to take programs, write small programs and compose them together, feed the output of one into the input of another. And this idea was expressed by a few different people, but in particular Doug McElroy, who invented pipes and who supervised the group in which Unix was born. And so this is what Doug says. This is the essence of the UNIX philosophy. It's 3 things. First, write programs that do one thing and do it well. So simplicity. The second thing is write programs that work together. That's composability. So these are the 2 whats, and then Doug offered a how. And this is what Unix does. Write programs that handle text streams, that are filters of text streams. So it takes a text stream in, gives a text stream out. And why do that? Because that's a universal interface. So this is Unix. So it's composability and it's usability. But it's not very good usability or composability, is it? Okay. So for example, if composability is based on text stream filters, what happens to my GUIs? Where are my GUIs? And here's an answer from the art of Unix programming. Despite popular mythology, this practice, that is text stream filters, this practice is favored not because Unix programmers hate GUIs. It's because if you don't write programs that accept and emit simple text streams, it's much more difficult to hook the programs together. Okay? So this emphasis is mine. It's much more difficult to hook the programs together. So here's a technique. We want to be able to hook programs together, in other words, composition. Well, here's a way to do it with text streams. But we throw out a tremendously rich world when we do that. So instead of sort of dumbing down our world to text streams, let's have it be not more difficult. Let's have it be easy to hook GUI programs together. So how might we do that? How do you compose GUI programs? You sort of know how to compose text stream programs. That's what Unix showed us. Well, my approach is a couple of main ideas. You can see one is just a translation of the pipe idea. So what's the pipe idea? And here's where I think what I'm describing and what Unix is different from visual languages, what's called visual programming languages. So there are two parts. Feed the output of one piece into the input of the next. Okay, that's the same as these visual languages. But the second one is different. Hide the intermediate data. Yeah, question?
So you're sort of something similar to Apple's automator?
I think that was the earlier question. Is this like Apple's automator? And boy, I wish I could answer that question. I'll have to learn what automator is. Maybe you can tell me later. So hiding the intermediate data reduces the complexity back down. And I'll give you examples of that. Now, so that's the first part is to translate the pipe idea. But the second part is I think, a fundamental shift and contribution. And that's to loosely couple interfaces and functionality. Okay? So we want something that's both usable and composable. And kind of the key insight that I'll be showing you here, the key trick is to have the user interface and the functionality together but separable. So loosely couple them. That way we can actually mutate the user interfaces when things are composed. Throw away things that are no longer, throw away things that are just about the communication. And I'll show you an example of that. I think I'll show you an example now. Okay, so this is a little rough prototype of a system called Eros, which embodies this composability and usability. So here are three little, you could call them apps if you want. This one is a uniform scaling function. So it takes in a scale factor and an image. These two are inputs, and this is the output. And here's another one, rotate. Okay. Here's one that's just an output, just a checker pattern. So what happens if I want to scale the checker pattern? If I want to combine these two pieces of functionality. In a Unix sense, what if I want to pipe this into this? Okay. Well, what I'd like is, the result is, well, I'll just show you right now. Start fusion. And here's the result. I've created a new thing, which is the fusion of the other two. Now, we'll take a look. What's absent is the input over here and the output here. That's what happens when you pipe. The output of one stage feeds into the input of the other, but neither is visible in the result. That's what keeps the complexity manageable as opposed to what's called graphical or visual programming languages. Another example would be if I want to feed this output into this input. Okay, confuse these guys. Now we get something that has attributes of both, and they're internally connected, but the interface parts, the output of one and the input of the other, have vanished. So that's a little preview. Now, in order to do that, you saw that the user interfaces were actually mutated during composition. That's possible because of this loose coupling. All right, so in addition to improving on the old beautiful Unix vision by having GUIs, here's some other things that were sacrificed in the old Unix dream that don't need to be. And one is graphics. Besides graphical user interface, there's a graphics period. Another one that's really important is to have a rich selection of data types, not just one. And that's a lot more convenient, and it's also safe. So especially if you have static typing. So it's much more convenient because it means I don't have to write parsers and unparsers as part of every single application like you do in Unix. It's also safe because it means that if in a statically typed setting anyway, I can compose these two things and know that that it's meaningful. You know, that I'm not going to core dump or whatever. And in addition, this approach that I'm talking about, as tangible functional programming, is scalable and it's consistent. And so in contrast, in Unix, there are a lot of mechanisms that overlap in purpose with pipes. And I've listed some here. Some may be obvious what the connection is, some may be less obvious. So standard input and output, clearly that's one mechanism. Arguments, program arguments, is another. It's a way of getting information in besides standard input. Sockets is another example. It's a communication mechanism. Threads is a concurrency mechanism. So pipes, the Unix idea of pipes involves not only communication but concurrency. Right? It's very elegant, very simple. So threads is an overlapping technology. And what I'm saying is that our programming paradigms, our programming structuring mechanisms have all this kind of stuff, and I'm picking on Unix, but I think all modern systems have essentially these things. And then I'm throwing in the C and the shell scripting language because they also are doing some of the same things that pipe does, which is composition. So whenever I define a function, whenever I call a function, I'm doing composition. So why have the second mechanism? It's because the first one didn't scale nicely. I skipped over this one, multiple arguments. So diff is an example. It takes in 2 streams and gives a stream. Oops. How does that fit into the pipe model? It doesn't. And so diff doesn't work like the others, so it doesn't follow the dream. So all of these can be fixed with what I'm calling a modern marriage, as opposed to Unix, a modern marriage of usability and composability. So now I'm going to move on to the second part of the talk, which is to give you a flavor of the Eros user experience. And I gave you a little preview of that before with the demo. So to dive into that, I want to say I'm taking a particular perspective on programming. And the implication of this may surface later, so you may have an objection to this slide later on. And so what I'm saying, programming is, for purposes of this experiment, it's a way to express 2 things. One is interface, and the other is functionality. Okay? So programming is about making these 2 things, an interface to functionality and the functionality itself. So from that point of view, you can think of programming as an authoring process. It's a creative process. So programming environment is an app. Right? It's an authoring app. And what it's making is, well, instead of music or video or cool 3D models, it's making interfaces and functionality. Now, if that's the case, then what is code? It's a command line UI to this app. Right? So this is a very old-fashioned sort of way to author things, is with a command line interface. So I want to suggest let's move into the 21st century and look at more concrete visual, sort of GUI-rich, a GUI rather than a command line interface to this app. So, and the code interface, the syntactic interface, it's very handy. We can do all kinds of things, store it in a file, run analyses over it, print it out. But it's also inessential. So let me put this really simply. The essence of programming has nothing to do with programs. Okay? Programs are just a means to an end. The essence of programming is making interfaces and functionality. Okay. So if that's what we're up to, I'm going to pick a framework which is functional programming. And the reason for that is, well, there's a few reasons. I love functional programming. It's also a very simple, a sort of pure, simplified, and complete formalism for creating these interfaces and meanings. Now, functional programming, I guess I'd like a show of hands. Who has sort of an idea of what functional programming is? Well, quite a lot of you. I'd say 80%. Who has done some functional programming? Wow. Wow, almost the same. Who actively does functional programming? Cool. Maybe that's why you came to this talk. All right. So another way to say what functional programming is, it's I think a little more description, is it's value-oriented programming. So in functional programming, everything is a value. Everything is a value, including functions. And if you look at it from a syntactic point of view, so semantically everything's functions. Syntactically, everything's expressions. You don't need statements. There's no need for sequencing. Because in a functional language, you don't do anything. So you certainly wouldn't want to do one thing before another. So this notion of sequencing is gone. So everything is expressions. And what I'm going to talk about for sort of succinctness and purposes, I'll address 3 kinds of values. And they're going to be atomic values, which will be things like numbers and images. So atomic doesn't necessarily mean small. And then secondly, pairs. So if I've got a couple of values, I can pair them up. And functions. And really, out of these building blocks, you can build anything. I'm not saying that you'd want to build everything out of just these building blocks, but this is a sort of complete framework. So Eros has 4 key essential ideas that combine toward this vision of usability and composability. And the first one is simply this: to use GUIs as a visualization of typed values. So when I think of a GUI, I'm not going to think of it as, this is the GUI of my app. I'm going to think of it as, this is a visualization of my value. So like the numeral 3 is a visualization of the number 3. Okay? So GUIs give another way to visualize things. And in particular, functions are very hard to visualize in strings, but they really fit very well with GUIs. So GUIs have sort of two parts. One is a structure that doesn't change with time, and the other is the dynamic content that does. And the same thing is true when you look at typed values. And you can translate this to, imperative object-oriented programming if you want. There are interfaces, which are static, and then there's the thing itself, the value or the function or the object that meets that interface, and that's more of a dynamic thing. So what I'm saying is that GUIs have the same dualism that our sort of semantic concepts have. So, and in particular, and this came as a surprise to me, or at least retrospect. Maybe the surprising thing is, why didn't I know this before? Which is that interaction and parameterization can be mapped to each other. So a function, I can think of something as a function, meaning I can create lots of things out of it, or I can equally think of it as an interactive thing. And I'll show you an example of that. Show you several examples of that. So this combination of the GUI that shows the structure and then the dynamic thing together, that combination I call tangible values. And I want to emphasize that I use the word values in the way that a functional programmer would. So tangible meanings might be a better way. I don't think there is a word in the sort of mainstream imperative programming world that it's in academia we would call it denotations. So it's the meaning of a program, not a program. So how would this look? This idea of saying that GUIs are visualizations of values, and the structure of a GUI corresponds to the type. Well, so there are three levels. I said there's atomic or base types, pairs, and functions. So what do base types look like? Well, they look like widgets. An atomic value is an atomic GUI. In other words, a widget. So here's an example. These are visualizations of a Boolean value, true, a numeric value, pi, and an image value, disk. So that part's very simple. Oh, forgot I had this. So next to pairs. So when we write pairs with textual syntax, we usually use a comma and a pair of parentheses. Now, a lot of languages don't have pairs as first-class values, but some languages, functional languages, do, and certainly in math you do. So the visual syntax for a pair is a horizontal juxtaposition of GUIs. Okay? So here we see three values. This one is of type pair of bool and number. This one is of type pair of number and bool, and this one is of type pair of number and image. So this is a visual syntax for pairs. And if you look, there are actually three parts. It has the one half, the other half, and then a handle to the pair itself. So this little vertical yellow slab is like the comma in the notation of pairs, or the cross in the notation of pair types. So what about functions? That's the third component to our calculus. And functions we lay out vertically. So a function has an input and an output. And we simply show the input above the output. Now something is going on here, because an input is a different kind of a thing. All right? So far, all the other parts where we see values. An input is something different. So let me skip over that for a moment. So functions not only visualize vertically, but they're interactive. So a function is visualized as an interactive GUI, where at the top, the input is something that I get to interact with, and the bottom is something that I get to see the results back. And now what do you do about multi-argument functions? Well, this is a very old idea. It goes back to probably the 40s, which is that every function is a function of one argument in this simple formalism. But if I want functions of multiple arguments, well, there are a couple of classic ways to do that. One is to have a tuple as the argument, say a pair. And the other is to do what's called currying. And this is an example of currying over here. So less than is a function of one argument, which is a number. And it gives me back a function of another argument, which is the other number. And that second function gives me a bool. So we have the usual curried and uncurried representations. I'm saying they map just very nicely onto this visual syntax. So let's see. I'll show you what some of that looks like. Well, I'll just use this example. So here we go. These are curried functions. Let me start with this one. So here's an input. And if you see, if I hover the mouse cursor over, I got input of type double. Here's another input of type, well, it's of type image. It actually says image bool because image is a, you can have images of any type. Okay? And it has an output of image also. So these inputs are sort of input and name only. I just, in this prototype, don't have a way to.
I didn't understand what you said about why it says image bool.
Okay, so because it's a very general notion of image that's parameterized over other types. So we can have images of colors. We can have images of bool, which you might think of as being a region of space or a black and white image. You can have colors with transparency. You can also have images whose pixels, so to speak, are 3D points or 3D points with normals. Now you get surfaces. Very cool. Okay, so I think I'll move on. So functions visualize as interactive GUIs. So the point that I want to drum this in. What you see here is a single static unchanging value. Okay? So I hope that maybe creates some dissonance, or if you're feeling some dissonance, listen to it, because this is important. That in functional programming, it's a changeless world. It's a stateless world. They're just, our values are. Nothing ever changes. Okay? So what the heck's going on here then when you see this thing turning? Well, what's going on is that you're looking at different slices of this function. So the way to visualize functions is to give the user access to the domain, to the parameter, which is the user's way of saying which slice of this unchanging value wants to look at. So it's unchanging in the way that like the sign function, or the absolute value function, is unchanging. This doesn't have state, just in the same way this doesn't have state. Okay. Yeah, question?
Are all integer inputs represented with a slide bar?
No. So the question is, are all inputs represented with sliders? And the answer is no. There's a lot of different representations. So here's one that's not a slider. This is an input. All number inputs. No, you can really roll any visualization you want as an input style or output style for any type. Yeah. So the examples you'll see in this talk will be mostly sliders. Maybe you might see a sort of type in or type out box for the same type. Thank you. So that first idea is visualize typed pure, that is unchanging values as GUIs. The second one is that to allow the user not only to play with these and explore these values, look at them interactively, but also compose them. And that's what makes this as powerful as programming. This is a key thing. And so how does this work? Well, it works by an idea which I'm calling fusion here. So what I mean by fusion is I've got two things, and I'll just show you this again. Let's get rid of that. I have two of these functions. And what I want to do is I want to fuse them together, make one thing that combines the two of them, feeding the output of one into the input of the other. And in the fusion process, some of the outward visible aspects of the two will go away. And specifically, the two matching, the input and the output. Because now that connection between them is internal. So that's what happens here. I'll say start fusion. And Eros gives me some choices. Here are three things that have compatible type. Which one do you want? And I choose this one. So this is a fusion here. Now, there's another way to play with this, which is I wanted you to know that fusion is an operation that makes a new thing. It's not altering things. Okay, just like pipe doesn't destructively modify, right, the two phases of the pipe. It makes a new thing, which is the combination. So maybe a user-friendlier way to do this is I'm just going to change the mode here. Now when I say start fusion and I click on here, those two things go away. So that sort of gives the illusion of them being fused together. But I wanted you to understand that it really is a constructive, not a destructive operation. Okay. Now, it so happens I don't really like this order of arguments. Now I've got a 3-argument function, or a curried function. It takes a number, an image, and another number. And it gives me an image. And I'd rather have the two numbers together. So I'm going to do another operation here, which is to flip the arguments of this function. So this is a function here. These 3 things together is a function. All of these is a function. These 2 are a function. So if you ever see something above something else, that pairing is a function. And here we see 3 such pairings. Okay? So I want to flip the argument order here. Oh, that's more what I like. And now I'd like to actually put this checker in here so I can start another fusion. And I get 2 offerings, and I'll pick this one. There we go. So now I can think of what I've made in 2 different ways. In the context of authoring tools, this is really intriguing to me. One way to think about what I'm doing is this is an authoring tool, or it's toward an authoring tool, that has the expressiveness of programming. And for instance, if you think of this as being like something you use instead of Photoshop or the GIMP, and obviously you wouldn't because it's so immature, but where it's going is it's a tool with which, in a very direct way, you can make not just an image using a filter. So let me put it in this way. Suppose you're an artist and you want to use this tool. Well, you're going to need to use some filters. Who do you ask for the filters? You ask engineers. Those engineers either have made them or they haven't. If they haven't made them, they may want to make them. Well, if you're an artist, an engineer doesn't work for another artist, and his values are very different. So it's very important to me that artists can make their own tools. And what's powerful is not the image, it's the parameterized image, it's the tool. Again, that's the difference between usability and composability, and that's why it's so important to put them together. So if you thought of this as a sort of replacement or evolution of the GIMP, then this is a GIMP in which artists make their own filters, not just images. So that's one way to think about it. Another way to think about it is they make interactive images rather than just images. That's pretty cool too. Okay. So that is key idea number 2 is fusion. And what happens in fusion? Well, we select compatible input and output. Those 2 disappear. Everything else remains and fused into a single TV. And that, I think, is what distinguishes this from at least most visual languages. So this is an example of what this looks like. If we have here's a function that takes a numeric input and gives an image. And here's something that is a numeric output. If we fuse those 2 together, we get this result. Okay, it no longer has any input and has this 1 wired into it. Here's another example. So I call this TV fusion subsumes function application. In other words, function application is a special case of fusion. Well, function composition, or what they call piping in UNIX, is also a special case of function composition. So here we've got this same function of a numeric input. Here we've got a function of a numeric output. We compose these together, what happens? Well, the input and output that match go away, everything else stays. And what I'm getting to down here at the bottom is that if you look at types, and if you look at function composition, if I start out with something of this type here, let me try this guy. Is that? There we go. If we start with a function, it has this type, and an argument that has this type. When you apply a function to an argument, you get something of this type. So these 2 matching pieces have gone away. Similarly, if you do function composition, here I have something that's my function that takes a real number, and here's another function that gives a real number. Function composition gives you a result of this type. So exactly what's happening with the UI elements is happening with the types. There's this direct correspondence. And this is an example of what I mean by, what did I? That GUIs and typed values have this parallelism. They have a static part, they have a dynamic part. And the composition, the types, correspond to the structure. So whatever happens at the type level is mirrored at the GUI structure level. So anyway.
So how do you specify the square root?
Let's see, square root function is specified as, so there's sort of an underlying collection of primitives. It's actually built on top of a language called Haskell, a pure functional programming language. There's a very simple way to take any Haskell function and a specification of a UI that's type compatible. So there's a little language of UIs, which I'll show you in a bit. Very, very simple language of UIs. And building blocks for that, and it's typed. And so I can build up UIs, and the UIs have their types. Like the type of this UI is function from R to region. The type of that UI is function from R to R. Okay. So also, though, there's something that goes beyond function composition, function application, which is we can reach deeply inside of functions. We can reach deeply inside of pairs. So here's an example of this is something that takes a number, and then its second argument, curried argument, is it takes a pair. And here's something that takes a number and gives you a single real. And I want to hook these up together. So that's something that I've never really, I don't know what to call that. It's not application, it's not composition. But that's something so this notion of fusion generalizes. It's quite a general notion. That's what I'm trying to say. And as always, if you look at these types here, you can see there's the input and output that go away. Okay. So, yes, please.
Has this any relation to Fudges?
To Fudges?
Yes.
So the question is, does this work have a relationship to Fudges? So Fudges is it's a functional programming library that was done in Haskell by a couple of guys at Chalmers. I'd say, yeah, it does have a relationship to Fudges. I think it's a much cleaner separation between the content and the UI than Fudges does. Boy, almost anything interesting that's done with user interfaces and functional languages has something to do with Fudges. It was just an incredibly rich dissertation. It's not a very informative answer. Maybe we can go into it more later. But I have to say yes. Right, let's take a look. OK. So back to the toys. So I've shown you some of this already. But I want to show you apply, compose filters. We did that. OK. Now, this is another thing that I think distinguishes this work from almost all visual programming language kinds of things, which is typically what's done in a visual programming language is you've got functions and values. And functions are visualized as boxes, and values are represented as flowing across arcs or segments, arrows. It's an inherently first-order visualization. In other words, the visualization itself makes a hard, visually syntactic distinction between functions and values. Ouch! What's powerful about functional programming is that functions are values. Okay? So that's what I mean by it's first order. So this system is different in a couple of ways. One is that visual languages with the boxes and arrows, every time you do a composition, you get something that's more complex than you had before. So the complexity grows and grows and grows. And visual languages are very sparse rather than a dense notation. All right? So pretty quickly you get just swamped. So you use up a lot of space not saying very much. Now, why doesn't syntactic programming have that issue? Well, it kind of does at the level of within a single definition. But when I compose functions, the interface stays small. And that's what I was showing in the previous few slides. Every time I compose two things, some of the interfaces of each go away. So there's not only an accumulation that happens, there's also contraction, there's also an elimination. So that's why, even though we do lots of compositions, our types or interfaces don't have to get huge, just our code does. Okay, but the code gets to be isolated and manageable. Most visual programming languages don't have that property. So this other property, which is even more fundamental because it's a semantic limitation, is this first orderness. And what I want to show you here is that this approach doesn't have it. It's fully higher order. So what am I talking about? So I've got some pieces here. Here's our checker. It has no inputs, just an output, so it's of type image. Here's a function. It maps an image to an image. It's a swirl function. Here's a translation. This takes a vector and an image and gives me an image. And again, even though I'm never tweaking this, it's sort of it's an input in theory. that you could think of, I could pull out a paint program here, or I could load in something. It just doesn't have to be happen to be wired up. So here's an example of a translate function. Okay, it's kind of interesting. I want to do something much more interesting. Here's something called hypertranslate. So translate takes a vector, but then it takes an image and gives you an image. Hypertranslate is much more powerful. It takes a filter. So translate, when you apply it to a vector, it gives you a filter. In other words, it maps images to images. Hypertranslate takes in a filter and gives you back a filter. So instead of moving an image, it moves an effect. So hypertranslate takes a vector and a filter, which in this case is the identity, and then it takes a region, an image. Okay? Now, let's do a fusion here. So I'm going to say start fusion. And what happens? Well, look what lit up. In particular, this one. So this swirl, it really has three parts: the input, the output, and another output, which is the whole thing. So we have access not only to its input and output, we have access to the whole function. That's what this little handle is for. So now I can perform a fusion. Okay? So now that input that was a filter went away, and my entire filter, the swirl filter, went away, because that was the argument. So that function was an argument. So functions as values is critical here. Now I get this. I get to drag the swirl effect around on this image here. Okay? That gives you a little idea, but let's give you more idea of what swirl does by fusing here. Okay? So now I want to replace this region input, this image input, with another one. And I'm going to pick this one here. There we go. So now all that I have left, the checker is baked in, the swirl is baked in, the vector input is still free. I could bake it in, but I'd rather not. And we could see what it looks like to move the swirl effect across a checker. Now, there are a lot of other things I could do. In particular, there's something called, this was hypertranslate. I could do hyperscale. So what hyperscale does is it scales a filter. Okay? So if I scale a filter, what that means is scale the, apply the filter to a kind of a bigger region. What it really means mathematically is very simple. It means inversely scale the input, apply a plain old filter, and then forward scale the output back. So if I did that, let's see, how am I doing on time? I think I want to not show that, but I can show it later if anyone's interested. So there we go. Now, I'm going to breeze through the mechanics here, and if people are really interested, talk to me, please. I love this part of it, but I don't know this is the best audience. I don't know if this is what you'd be most interested in. And also I have a paper that really focuses on this. But here's the key idea. And I said this before: loosely couple the interface with the functionality. And so here's the simplest possible way I can imagine saying that. So a TV, a tangible value, is simply a pair of what I call an output. Okay? So this is Haskell code. This means it's defining a type called TV, but it's not really a type. It's like a generic in Java. It's parameterized by another type, so it's a family of types. So this says an A-valued TV, where this could be double, image, whatever, function. So a TV of type A is two things. It's a pair. One is it's a way of outputting an A. That's the GUI. And it's the A itself. Okay? So this is what I mean by a loosely coupling, is that instead of writing code that has the UI and the functionality all munged together, right, that would require brain surgery, in other words, would require a skilled programmer to disentangle, just never entangle them in the first place. This is a very simple idea, and it works very well. Now, every operation that's done, where you see this is sort of the fusion in particular, every operation that's done is done on each of the two halves. So when I want to do a composition of TVs in one of these fusions, what I do is I simply fuse the UIs and I fuse the values. So in particular with function composition, no, let me do the application because it's simpler. If I have a function application, then I'm going to have a function valued UI and a function value on the one hand. And I'm going to have an argument valued UI and an argument value on the other hand. So when I want to compose them, apply. I apply the function to the argument. That's very simple. And then I do something that's analogous to it with the two UIs. So the key idea is combine them for convenience, but keep them separable for composability. Okay, now you couldn't do this in Unix. Unix gives you composability, but it still is generating and parsing these character streams, right? So this approach actually eliminates the generation of the output and the analysis of the input. It directly wires the semantic. It makes a direct semantic connection. So how does this work? Very, very simple. Remember I said there's 3 kinds of values of interest: base type values, pairs, and functions. So similarly, there are 3 kinds of GUIs. Okay, so this is a little algebra of GUIs, and it has those 3 things. Here's a primitive. Here's a widget. Okay, put. Think of a put it's a type I'm not going to explain. There's a lot of detail. Put is something that understands how to put up a GUI element. Okay. So if I know how to, in particular, a widget. So if I know how to put up a widget, then that gives me, I can wrap that up with this thing called put, and that gives me a way to visualize an atomic value. So that's what out is, a way to visualize something of type A. Now, given 2 visualizers, I can make a visualizer for the pair. Okay, and you've seen that as horizontal juxtaposition. I might have actually only shown you that for inputs, but it's there for outputs as well. And what is lambda, this thing I'm going to call lambda? Well, that's a way to build functions, build visualizations of functions, not functions themselves, but visualizations of them. So if I have, oops, this one's not an input, it's not an output, it's an input. So if I have an input for alpha and an output for beta, A and B, then combining those 2 things together, stacking them vertically, gives me a way to visualize functions from A to B. So how do I visualize a function? Simple. I give the user a way to tell me what input value he's interested in, and I give myself a way to tell him what the corresponding output is. Okay, so there's a new thing that comes up, which is input. So input has another little algebra too. It's just 2 things. It's atomic widgets and pairs. Okay, so this is a sort of complete little algebra, a little set of building blocks for building UIs of any of these values. And the neat thing is that the structure is that the operations that happen at the semantic level for composition have corresponding operations at this level. And now, putting those 2 things together, we get TVs. We get to manipulate TVs, which simultaneously manipulates user interfaces and values. And I'm going to give you, here's another view on it, and then I think I may just stop there and ask for questions, which is that you can also look at all of this as MVC. So what I've just showed you, so this slide is just the previous slide with some different names. So I'm going to use these names, classic names, model, view, controller. So a model for a value of type A is just an A. In other words, this is just a name I'm introducing that it doesn't add anything except to remind you of this idea of model, view, controller. A view is one of these outputs, and a controller is one of these inputs. So again, this slide says exactly the same thing the previous slide does. So now an MVC, I'll call it instead of a TV. An MVC for a type A is one of these, is just a pair of a view for a type A and a model of type A. And remember, a model of type A is just A. Okay? So an MVC, so this is an interesting little way to cut MVC. It doesn't have 3 parts, it has 2 parts. MVC really has 2 things, a model and a view. But views are sometimes made out of controllers and views. So that's what happens here. So a view is you can make out of a pair of views, but a function value view you can make out of a controller and a view. And similarly, controllers can be atomic, or they can be pairs of controllers. This is another way to dice this. So I think that I'm going to skip past the rest, which is very technical, and just get on to the conclusion, which is I think we can have a rich marriage of usability and composability without a terrible compromise like everything is text streams. As we can keep what's really sort of wonderful, modern, powerful, convenient about modern programming languages and about modern user interfaces and put them together. And the heart of how I do it is with this, of how I do it in Eros, is this idea of fusion. And it doesn't have to make the compromise because I don't go for a universal interface. And to make this work, we want the GUI and the content to be together but separable. Okay? They're together, but they're never entangled. And there are a bunch of things to explore. One of them is, what are the implications of this idea of composable MVC? Another is how does this translate to really the kind of classic setting of MVC, which is object-oriented and imperative? I don't know. And another one is, if I say GUIs are types, well, that leads me in a really interesting direction, which is I have a set of sensibilities about how to design programming interfaces. I make them really simple, really pure, really composable. Well, have people really thought about designing user interfaces? Now, if my goal for a UI, I'm changing the game back to the original one. If the game of my UI is to make a really nice user interface for a customer, right, for a user, rather than just a way to visualize a pure value, which is more like a kind of programming language angle. But do the sensibilities that we developed for making really nice, elegant, composable, simple, powerful programming interfaces translate into UIs? And I conjecture yes. And so this is a thought experiment. Take a user interface for a realistic application. Now imagine that this user interface is a visualization of a pure functional value. And the question is, what the heck could that value be? What's the type? What are all these things doing here? It's very complex. I would never design a programming interface with that complexity. And it's not only complex, but it's specialized. It's not very composable. It's not as general as I want. So my conjecture is that if we go through this exercise, it'll tell us we really want to redesign our UI for our application, get into something that's more simple, more composable. I don't know. I think it'd be interesting to pursue. So I'm going to stop. I'm going to stop right there. Take any more questions and. Okay.
So one of the things that I do when I'm programming is I make a mistake and I look at what I've typed up and I say, oh, here I passed in x. I should have passed in x minus 1.
Yeah.
With Fusion, I don't know how somebody would determine that happened if they fused a bunch of things together and got unhappy with the outcome.
So I'm going to try and repeat what I think is the essence of your question, then you can correct me and tell me what it really was. What I think you're asking is, what happens to this nice feature of syntactic programming, which is I get not just a result, like the running thing, but I get to look at basically a recipe for it. And in that recipe, I can find the thing I want to change. Okay? Whereas what I showed with Fusion, all you're left with is the end result. How do I go back? How do I see what it was that I even did? How do I get back to it and change it? And I would say, I don't know. What appeals to me is to ask the question of what's a really user-friendly way to do that. Okay. So I want to find an answer to this question and stay in this world of concreteness, directness, rather than going into the world of abstraction and syntax. This sort of very indirect way to get to meanings. And so one idea is just a weird fantasy idea is have an interface that's like a video camera, right, on you, doing this experience of putting this thing together. When you want to look at what you did and what you'd want to change, go back and look at this movie of you doing it and edit the movie. So I mean that sort of metaphorically, but that would be the user experience. It would say, here's something that's sort of like a movie of you doing this. Go back and change the movie. It's just an idea. I have no idea if it's a good idea or a bad one.
LabVIEW at all?
LabVIEW is a little bit. It's one of these visual languages with boxes and connectors.
Yeah, it's built for physicists
Yeah.
who are used to having dials that they tweak on their physical things. And so they have a dial pane where you've got all your knobs and your registers and stuff. And then on the back is the wiring pane where you connect up the components.
So say it again. So one side was...
One side is the dial pane where you've got the dials and your knobs and your gauges.
Okay, so I've got two
On
views.
the
One is
other
of the
side,
inputs.
you've got the wiring on how you hook them together.
Oh, I see. So one side has the inputs and the outputs.
Yes.
The other side is like this, all these patch cables that go through processors and connect up things.
And
Okay.
so you have graphical representations of each of these, and you can blow up one of them and look at the, instead of just having an IC that you're wiring to, you can actually blow up the IC and see what logic is going on inside of that chip.
So there's some concreteness. There's the kind of outer view, inputs and outputs. There's the inner view of all the wiring, which is kind of like the code.
And for you seem to be far more interested in the type theory involved. And there's an interesting connection between string diagrams, or say like Feynman diagrams, interactions of particles, that sort of thing, and flowcharts and the way things are hooked up together. A guy named John Baez is a mathematical physicist who does category theory, which has direct connections to higher order type theory.
Okay, so I want to interrupt
I can
just
give
so
you a
that
link
people who
for
are
that.
doing video conferencing can know what you're talking about. Okay, so just for the sake of other people who are listening and might not have heard the question, you're pointing out that that in addition to the sort of lab view, there's also the world of string theory and techniques and theory there.
String diagram.
Okay, string diagrams is used, and that there's some relationship between string diagrams and higher order types.
Yes.
Okay, I didn't know about that, and I'd really love to get a pointer.
Symmetric monoidal categories encompass both lambda calculus and string diagrams. They're common structures.
Symmetric monoidal categories is a place to look at connections between higher order types and string diagrams. Okay, cool, thank you.
And so that would fit. It would show you the structure of your program, which would answer his question in how do I see this? What am I doing?
So
You'll
so
see
that
all of these
connection may give us a way
components
to...
hooking together in a diagram.
Cool, thank you. Okay, I think we're out of time. Any other questions, grab me afterward, but... Oh, downstairs would be great so we can free up this space. Thank you very much.